Going on to this slide then, as you can see on the left-hand side at the top there, those are the issues that I was discussing, the limitations of traditional production lines that Masterly is attempting to address. And below that, you can see a set of objectives that we've targeted, which is to, I won't go into these in great detail because largely these are technology based and the purpose of today is to focus on the social science. But obviously you can see objective 3 is to develop user-friendly interfaces for robotics machines, control and programming. But as I will explain as we go through, the human-centered or user-friendly approach crosses other aspects of the project more widely. So just to go through our use cases in Masterly, we have the Kleeman elevator control electrical cabinets assembly use case that you introduced, Marta, earlier on. So the current state is obviously a very highly manual operation involving quite small scale assembly, and the vision is to move to a more collaborative system which would reduce the need for manual application of manual tasks that are unskilled, repetitive, not particularly healthy, not very enjoyable for the human operator to perform, thereby enabling them to focus more on the more skilled and cognitively satisfactory tasks. And we have some KPIs that are beyond the ones that I've listed there. I'm focusing very much on this in this presentation on the human-centered aspects. So we're aiming for reduction of manual tasks via the implementation of robotics by around 50% improvement, productivity in terms of cycle time reduction of a 40%, which isn't necessarily a human-centered approach, but it relates to the other issues below that, which is to focus on psychological impact and increasing worker acceptance of the new systems by 15%. And the cycle time reduction is also a key driver of improved ergonomics by reducing task time and musculoskeletal risk. So reducing the amount of time that the operator is engaged in posturally or physically demanding strenuous activities that are not very conducive to well-being. Moving on to the decathlon sportswear logistics and packaging use case, we have the current state where manual operators walk through large areas of a warehouse and pick orders, individual orders for packaging and sending out to customers. And the Masterly vision is to automate this as far as possible. Reducing manual strain like the Kleeman case, and to focus on improving the human enjoyment of the task, allowing them to focus more on the quality control and skilled aspects of the task, and removing the physical manual handling strain. And again, we have a productivity and performance target of about 80% improvement by reducing the manual tasks using automation. In reducing cycle time reduction, increasing, in this case, worker satisfaction as well as acceptance, and by, again, the 15% reduced musculoskeletal risk target. And then finally, I do apologise. Oh, no, that's right. So the Aeronova task, use case task, is currently a task that involves quite heavy manual handling, moving large components in aeronautics around. And our target is to implement a human-robot system, which actually is not as collaborative as the other two use cases, because the aim here is to replace that heavy manual handling and the risk of injury and collision that it involves, focusing on allowing the human to conduct the smaller assembly tasks, the more cognitively skilled tasks, and take away that dangerous heavy lifting. And again, there you can see some human-centered KPIs, and the description of the improvements that we're trying to achieve there, very similar to the other ones. So moving on to what we are doing in terms of the human-centered analysis. In work package 1, it's worth mentioning we engaged in some user-centered requirements capture. And then in work package 4, we focus on user-centered design of interfaces. And for that, we have adopted a 3-stage or 3-spoke methodology. One aspect of the methodology is to really focus on understanding what the human currently does. We believe that it's very important to, before doing any design and implementation work, to understand what the tacit skills involved in operations are. We can look at standard operating procedures and work standards to understand what the system designers intended people to do, but we know that people don't tend to do stick to those very rigidly. In many cases, there's often deviations from standard operating procedures. For good reason. We know that operators tend to adapt things because they want to make it better, easier for them for personal reasons. Maybe it could be their physiology or their natural abilities, or it could be that they find a better way than was originally designed. So we want to understand that, and we use eye tracking for that, where we get operators to perform their tasks wearing the eye trackers, which gives us operators' own perspective of the task being executed. It gives us a good combined field of view, horizontal and vertical view. And we have these systems that involve, the eye tracker systems that involve accelerators, gyroscopes and magnetometers, I can't say it, which accurately track their eye gaze and compensate for head movement. So we get a very accurate video recording, but also a microphone recording the verbal communications, which gives us additional detail. Excuse me. This gives us some various outputs, including those examples that I've put there in the small pictures. Some heat maps, which show us how much people look at certain areas. So it shows us the intensity of where specific parts of the field of vision are concentrated on. That's important because it shows us what grabs people's attention, and therefore this could indicate, it could be explained by areas of the work naturally, but if we ignore that, we can also look at how that might infer that these are areas of problems and issues, for example, where they might need to really focus on something to get it right, or because there's some confusion. We also look at dwell times in that middle picture there. That's an example of where we can see how people have looked at things for a length of time. Again, that may indicate where there's a problem because there's extensive decision making needed, some confusion, etc. And we can also look at scan paths, which is the order, the sequence, if you like, in which different areas of a field of vision are looked at, and that indicates what gets people's attention first, or cues to action, what they then need to do next, and so forth. And these are really good indicators of the current manual task, how it's being performed. They tell us where those problem issues are, and that then can advise us on where we may need to design out problem areas, where a robot would actually be more beneficial because it could be designed to take away some of those problem areas, or where the actual manual process itself in the human-robot interaction needs to be redesigned. So this analysis shows us the areas of the task and environment that demand greater attention, decision-making, that are prone to error or difficulty, or those that are effective cues to aid awareness. And we find that eye tracking not only gives us that objective output, we can also use that recording for playback to the operators if we want them to tell us how they do things. And so because a lot of what they do is so based on tacit skills and non-technical skills, they're not always aware of that procedure. It's like we always use the example of driving your car to work. There's a lot of aspects of that journey that you wouldn't be able to tell us if we asked you to tell us about it, because it comes naturally. But if you recorded it, you would be able to then explain, well, this is the indicator for when I turned right. This is, you'd be able to then recall more about that, the decisions you made and the task process you undertook. Excuse me. So the second part of our work package for user-centered analysis was to conduct hierarchical task analysis, and that's based on the eye tracking videos. Hierarchical task analysis deconstructs manual processes into individual component steps at various depths of scrutiny that suit the analysis, and it helps us reveal deviations from standard operating procedures. It helps us identify those decision-making points. Helps indicate the process change potentials where there may be, again, we identify those problem areas and where we might need to design those out when we redesign a process to use a robot. We also use task decomposition, which is an extra layer. It extends the HTA by providing another layer of analysis that classifies steps into things like cues, decisions, actions. And so we can identify the steps that utilize tacit knowledge and skill. And that's important because tacit knowledge is often the part of a human operation that shouldn't be maybe transferred to robotics. It's that sort of skill and creativity that only a human can bring. And it helps us highlight error points and then identify remedial actions that we can integrate into the redesign of the process. This analysis shows us the specific steps of the task that are problematic, that helps us to engage in user-centered design and more effective function allocation. The third part of our user-centered analysis is the application of psychometrics. So we use psychometrics, as you all know, to capture current levels of psychological states, indicating potential areas of concern in the current processes. And also this provides us with this quantitative baseline data set against which we can measure impact in future assessments. So gathering a baseline of how people are responding to the original manual process means that later on when we implement our solutions, we can then measure again and we can assess the differences. And so we can hopefully, it's improvement, measure those impacts and assess whether we're achieving those KPI targets that I mentioned earlier. We use various psychometric tests. We tend to use reliable and valid assessment tools that are already available because they have proven validity and reliability levels. And so three key ones that are used in Masterly here are the physical discomfort scale, because we want to assess the difference in ergonomic, postural, physical differences between the as-is manual task and the to-be one after we've implemented solutions. We measure mental workload because we know that's very, very important to how people, how satisfactory a new system is. And we are not targeting blanket reduction in mental workload at all. We measure 6 dimensions of current mental workload using the NASA TLX, and we use that because we know there are optimal ranges of mental workload. We don't want to go for too little workload because we know that then is unsatisfactory, and we don't want to overload people. So we need to get that optimal range. And we also measure situation awareness, which we also know is very important for automated systems. People need to understand what's happening at any given time. So we want to ensure that we also achieve an optimal level of awareness in relation to task characteristics. And this analysis overall allows us to understand the physical and psychological impacts of the project solutions and quantify them. So those three together allow us to understand the user-centered design of interface, to improve it, to understand what needs to be allocated to a robot better. In work package 6, we are undertaking a methodology, we're defining a methodology to assess operator acceptance and psychological impact. We have our tried and tested methods, but we understand that these are often quite generic, and we want to apply them to the specific context of Masterly and then understand how they might be developed for industrial systems per se. So for that, we are undertaking some exploratory studies in the use cases, because this is the only way we can get a fundamental idea of how people envisage systems being changed. And when I say people, I mean the subject matter experts, the users themselves, the end users. They are our experts in these manual processes, so we want to utilise their input as much as possible. So we put the end users and operators into small groups in human-centred and ask them to undertake human-centred design activities, which is to co-design and redesign, if you like, solutions. We give them stickers and graphical activities. We show them videos and give them creative materials to use. There's some examples on the right-hand side in those photographs there. Excuse me. We also use that opportunity for group discussions and brainstorming, using a semi-structured format which allows them to freely speak and generate their ideas. And using this method, this kind of free and flexible method, they can locate successful and problematic task environment characteristics. They tell us what works, what doesn't work, what they want to see, what they don't want to see. So that it gives us the as-is current state viewpoint, but also what they envision for the future. It allows us to capture their attitudes and perceptions related to the acceptance of new technologies and processes. So we can also, at this opportunity, also give them some of those psychometric scales that I described in the last slide, so that we can also sort of get a gauge on how they feel about these their tasks in that way. And we can identify change management enablers and barriers, those things that they tell us that we know is going to optimize the integration of the new systems, and what are those things that might prevent them, so we can work on those. Excuse me. So the analysis provides us with qualitative data from real operators or end users that indicate the key human factors that we need to focus on in specific use cases. And as we do that, the key part of these exploratory participatory design workshops is it engages the workers. They are giving us their feedback on these new designs that are going to be implemented, and that means that they start engaging. They can see their feedback being implemented as the process goes along. That optimizes buy-in essentially and their acceptance of the new systems. We also engage in experimental studies, and we are now at the stage of just starting to begin these. And these are for targeted assessments of prototypes. We base them on the exploratory results, in that what we've learned in those participatory design workshops and focus group discussions beforehand help us to understand the issues that we need to focus on. But we also need to look at specific aspects of those objectives that I presented right at the start of the presentation, which is looking at the interface and communication modes, looking at different types of grippers, and also taking behavioural measures. So it's things like the task time, remember the cycle time that I mentioned, looking at errors, and looking at those that broad range of issues that we know we need to look at. In those experimental studies, we will measure physiological and psychological reactions in different conditions, so that we can triangulate these multiple methods. We include the eye tracking, as I've previously described, because we can use eye tracking in experimental conditions as well. We measure stress responses such as heart rate, skin conductance. Sorry, I've spelt that wrong there. We can measure neurological activity responses, so the frontal cortex blood flow measurements, which indicate stress and decision-making activity. We can analyse facial and emotional changes, and we can also use motion capture for physiological analysis as well, and we can feed that into CAD modelling as required. These various techniques we support with qualitative data collection as well in experimental conditions. We know we should never rely just on objective measures, because they tell us how much things change or are changing. They don't tell us why. So we always triangulate with qualitative assessment as well. So when we measure, for example, heart rate and skin conductance, and if we see deviations and variations, we will accompany that with questioning people, interviewing them, and asking them why things changed at those peaks and troughs and times as well. so that we understand not only the how much, but also the why. Okay. Moving on to work package 7, which is the final work package I'm going to talk about in terms of human-centered analysis. This concerns standardization, and it's about creating a roadmap towards human safety in standardization. And as you can see from the clip from our general agreement there, we're aiming to focus on 3 main aspects, which is understanding the open or vague areas or missing norms. So what that means is we want to understand what guidance we need that is not in current standards, because current standards regarding robotics are there's very scarce attention to any psychological or emotional impact on users. It tends to focus very much on the technology and the engineering side of the systems, which is has been absolutely apt, but with increasing human-robot collaboration and human interaction between people and robots, we know that needs to change. So we want to do a review of what guidance is currently not, that we need for these new systems that's currently not in standards. And we're going to do that by undertaking assessments with technical partners, consulting and surveying our partners and other experts to map our requirements to existing standards. To understand exactly what we need in new systems that isn't currently covered. The second part of that is updating existing standards. Well, we can't do that. Hello?
Oh, sorry. We are running a bit out of time.
I'm going to finish off very quickly. Okay, I'll speed up my chat.
Sorry.
Okay.
Sorry.
Okay, so we'll look at which standards need to be addressed, and we'll do that with identification through existing contacts. We can't automatically update existing standards by any means, but we can understand which standards need to be addressed and consider the guidance needed. And also we need to demonstrate our compliance with the existing standards and understand those gaps. And we'll do that roadmap through I'm involved in existing standardization through those roles on the right-hand side there. And I think the interesting thing there is I'm perhaps the most important thing is my liaison between TC299, which is robotics, and TC159, which is ergonomics. Moving on very quickly, sorry, this is due to the technical issues at the start, I imagine. I won't talk about the first 2 there, 10218 and 22183, which is work that's either just been released or currently under development, because again, those are very technical topics and technical standards. But I will focus on the bottom 2, which is the CWA, which is one that I authored in a few years ago, which basically sets out standardization of methodology for developing psychometric assessments relative to industrial automation contexts. And we are going to be extending that in Masterly. And also to mention the BS 8611, which is a British standard, but it was the world's first robot ethics standard. And we revised that in 2023. And that provides a framework for ethical risk assessment. And in Masterly, it will form the basis of a new tool for design and integration. So very quickly, summarising, I won't go through all of this, but as you can see, there's a range of outputs that we're aiming for there, and achievements that we're aiming for in the project. So thank you very much, and sorry if I've overlapped. Thank you.
Thank you, Sarah. Don't worry. Okay, so now, last but not least, we have